Okay, so we looked at the energy balance with these simple models of taking incoming solar energy, which is often referred to as absorbed solar energy, and emitted terrestrial radiation, which is what we have to balance. So if we looked at a simple model where we had no greenhouse gas and we ended up with a temperature of 255 Kelvin, which is too low at the surface, but when you add one layer we got 303 Kelvin, which is too high, and then we added multiple levels and said you can derive a more complicated relation. The main message was that because of greenhouse gases, the surface temperature tends to be warmer than it would be in the absence of any greenhouse layer blanket. Okay, we mentioned Mars, Venus, Earth, as you know, is known as having the Goldilocks blanket, neither too warm nor too cold, just perfect, because so far this is a place which has abundance of life, as we know. Of course, now there is potentially life possible in other places on the solar system as well, in moons of certain planets, maybe on some planets themselves, and so on and so forth. So the second model here, looking again at the number with one greenhouse gas layer, we got surface temperature of 303 Kelvin. We were looking at total solar energy coming at 342, about 30% being reflected, 102 watts per meter squared. So this is a graphic rendition which gives us a better sense away from the equations, so that those who are not into equations can still get a full sense of what we're talking about. So part of the energy coming from the sun in the shortwave is being reflected because of the albedo. So absorbed solar radiation, ARS, is 240 watts per meter squared, which is coming into the atmosphere, and we will see it's distributed within the system. So the outgoing long wave radiation at 255 Kelvin then can balance 240 watts per meter squared coming in, and that occurs as emitted terrestrial radiation sigma Ta to the fourth, and there is some that escapes directly from the surface without getting trapped in the atmosphere, and that is emitted terrestrial radiation at sigma Ts to the fourth. So if we didn't have greenhouse gas layer, then obviously surface outgoing long wave radiation would be doing the job of balancing solar radiation. Okay, so energy balance for the atmosphere is emitted terrestrial radiation from the surface equals 2 times emitted terrestrial radiation from the atmosphere, because atmosphere is putting some back to the surface and putting some out to the surface, so that is both directions, so that is twice. So sigma Ts to the fourth then becomes 2 sigma Ta to the fourth, which is a simpler way of looking at. So if you derive surface temperature here, then you will see that it will be greater than Ta, because it has a factor of 2 to the 1/4 that gets multiplied, as we saw before. So in reality, life is a little bit more complicated. So the surface temperature is at 288 Kelvin, 15 degrees centigrade. The bouncing around of energy is a bit more complicated, as we will see. So incident solar radiation 341, 342 depends on when you are doing this figure, for example. So you have 79 going here, bouncing off of the atmosphere, and 23 bouncing off of the surface. So the total albedo is still about 30%, so 102 watts per meter squared, going straight back to space without doing any work, without warming anything, without energizing anything. So you have 78 that is being absorbed in the atmosphere at various levels. Remaining 161 is going to make it to the surface. through the atmosphere. We will see that there is a lot of details there as well. So sensible heat is about 17 watts per meter squared. Latent heat is 80. 356 is emitted from the terrestrial surface. So you have to remember that the numbers, for example, if only 161 is reaching the surface, how are we getting such large numbers? We will see that energy can bounce around. What is the best way to think about it? Think of yourself under the blanket. If you feel cold, you're going to put on a blanket, and the blanket is what is it doing? Unless it's an electrical blanket, it is just trapping your own body heat and raising the temperature. If you didn't have the blanket, your body heat would be lost, but with the blanket, that heat is being trapped, so you can feel warmer. That's kind of what happens here. So the big picture, of course, is that the what is received by the Earth has to be sent back. So those are the numbers here. So emitted by the atmosphere, so that is absorbed terrestrial surface radiation going down, and so that's 396 emitted terrestrial surface going to be 356. So 40 is the atmospheric window, so that's the difference between 396 and 346. So here you have the difference of 239 to 199, which is also the atmospheric window. So if it doesn't make too much sense, then look at this figure. Maybe this helps, done a little bit better than this figure. I don't want to criticize anybody, but nonetheless. So here we are again, slightly different number for incoming solar radiation. Clearly mentioned, absorbed by the atmosphere is 77.1. Reflected by clouds and the atmosphere is 77. Reflected by the surface is 22.9. So we are still about 30% albedo. The rest of the energy absorbed by the surface is 163.3, and net absorbed here is 0.6 because you are moving energy into evapotranspiration. So that's 86.4. So that is the latent heat, which is evaporation and evapotranspiration. Evaporation is basically molecules of water being pulled out of the lake, soil, and oceans, and evapotranspiration is basically water that is cycling through the vegetation before coming out as water vapor. Okay. Thermals, conduction and convection is a small number at 18.4. What else is going out? So emitted surface radiation is 398.2, out of which there is some atmospheric window that allows 40 watts per meter squared to go out. Clouds emit about 29.9. Atmosphere, after doing its energy downward, upward, everything reaches some temperature, as we saw. It's going to emit 169.9. So that leaves you 358.2 that is absorbed by the atmosphere. Okay, so you can see that we are not talking about simple situation of changing temperature and OLR and a short wave, outgoing, long wave and short wave anymore. We are doing many things like evaporating water, vegetation, evapotranspiration, thermal conduction, and greenhouse gases, which is a critical part. They are putting 340.3 watts per meter squared back to the surface because they have ability to absorb the outgoing long wave radiation and get warmed by whatever is absorbed by the atmosphere, and create radiation going in both directions. But going out is not as simple as we said before, coming down being equal to going out. So coming down here is 340.3 and going out from the surface is 398.2. Okay, so net what comes out here is the difference of the two numbers here. So 340 coming in, 77 plus 22.9 reflected, and the remaining 239.9 is the total outgoing infrared radiation. These numbers have to balance. What is coming in, what is going out. 1, 2, 3. Short wave going out from the atmosphere and cloud, short wave going out from the surface, long wave going out from the effective height at which energy goes out. So a lot of bouncing around of the energy, and you get numbers that are much larger than the net energy that is coming in. So Earth's energy budget describes the various kinds and amounts of energy that enter and leave the system. It includes both radiative components in light colors and heat, which is the infrared energy in red. They can be measured by satellites like Ceres and other components like conduction, convection and evaporation, which also transport heat from the Earth's surface. On average and over the long term, there is a balance at the top of the atmosphere. The amount of energy coming in from the sun in yellow and is the same as the amount going out from reflection of sunlight and emission of infrared radiation. Okay, I hope that kind of seals the deal in terms of what really happens in nature. Obviously, it's very hard to balance, and not everything can be measured directly, so you are often deriving quantities like evaporation, and evapotranspiration is even more difficult. Convection, etc., thermal conduction and convection are also hard to measure directly. So often you are using indirect evidences or other variables to compute net fluxes. So you always end up with residues, and you have to remember that within a year this balance need not happen, because the ocean can store the energy and release it later. We are only talking about energy going from the surface, absorbed in the atmosphere in terms of short wave and long wave, emitted by the atmosphere as heat downward and upward and so on. Ocean, which has a memory, can delay these time scales. So you have to average over a certain time scale to look at this balance. And adding greenhouse gases, which is what is the main topic of discussion now, day by day, every day, that changes how much of the heat energy is going out and what imbalance is being created in terms of the net energy coming in and net energy going out. So we'll add a few more details as we go along. Okay.